that'll be a hard act to follow. But yeah, I'm Andrew Wildman. I'm here to talk about student-driven research and what that means for the academic AI and ML sphere. Okay, so first of all, I am a chemistry PhD student at the University of Washington. But when I'm not doing that, I'm also the president of the University of Washington Research Computing Club. What that means is we are a student organization. We have student HPC resources that are entirely student funded. That means that students can get onto these. They can do exploratory research completely unrestricted by any sort of PI funding. We think that this enables a bunch of innovation, a bunch of learning, and it really benefits research overall. In particular, we found that one aspect of AI and research that's been benefited from this is the unification of traditional AI tools and computational science techniques. So I'm going to go ahead and highlight a recent publication that demonstrates this. This is called Fantastic Liquids and Where to Find Them. This is the actual publication title, done by Wesley Beckner in the Fettner lab at UW. Okay, so the goal of this project is to design a new ionic liquid with optimal heat transfer properties. Why we would want this is for things like thermal solar concentrators, where we want to take the thermal energy from the sun and move it somewhere else. Unfortunately, traditionally, molecular design has been a very, very challenging problem. It suffers from the curse of dimensionality because you can put atoms pretty much anywhere in space. And also, physics-based simulations take a long time, even on high-performance resources. So we're going to go ahead and try to use AI and ML to solve this problem. In order to do that, we need to tackle three challenges. One is, how do we estimate properties given a chemical structure? How do we generate new structures based on that? And finally, how do we validate the properties we're getting out to make sure that this isn't some sort of extrapolation error? The protocol that Wes came up with is called adaptive learning and design. This is a technique that really just takes three different ideas and puts them in one. It takes adaptive learning, traditional optimization techniques, and physics-based simulations, and wraps them all together. So in particular for this project, we need to first model the system, get the properties out. We do that through something called a quantitative structure prediction relationship neural network. Basically, you just throw in a molecule, it should be able to, and you retrain it, it should be able to predict a property. We're going to use two of these, one to predict heat capacity and the other to predict density. Now, because this is so much faster than the physics-based simulations, this allows us to use genetic algorithms to go ahead and mutate these structures based on an encoding called SMILE strings. This generates chemically reasonable structures which we can then target properties. Once we have found the structure that gives the closest prediction to the targeted property, we can go back and actually do a physics-based simulation on that system and make sure that we're not getting it completely wrong. So what does this give us? Let's explain this figure a little bit. The black dashed line here is the known experimental boundaries for heat capacity versus density. We don't know any, we don't have any experimentally validated results outside of this. The red are the targets for optimization. So you can see that we're trying to target places usually outside of this boundary. The purple are predicted properties from the neural network, and then the green is finally the simulated physics-based simulation properties. There are two conclusions we can draw from this. First of all, the low heat capacity boundary emerges at this target prediction interface. It's important to note that the two neural networks that we were using aren't related in any way. So this comes out of just the straight up physics that's being modeled here. And finally, there are some ionic liquids that we can validate with physics-based simulations that lie outside of this Pareto front. So finally, to summarize, I think that the big takeaways from this are that, one, when we use traditional AI tools coupled with computational simulation techniques, we can get much more powerful insights than either of them on their own. And finally, all of this work was done and enabled by the student-funded resource at the University of Washington. So if you allow students to explore their own ideas in a very low-risk environment, you can get powerful solutions out. Thank you.